Normalizing. So the normalizing, it's a similar process of full annealing, but the cooling is established in air. Because in full annealing process, that the cooling process can be taken place in the furnace itself. But in normalizing process, the cooling can be taken place in normal atmospheric air. So full annealing is an expensive model and the time-consuming process where reasonably soft and ductile material is required and cost of savings are desired. Then the normalizing process is used instead of full annealing. Steel is heated up to 50 to 60 degree above its upper critical temperature and the normalizing process can be taken place. So, what is the difference between normalizing and full annealing? Because full annealing we have that already completed, but the normalizing process. Normalizing is more economical than full annealing process because there is no furnace is required for cooling. But full annealing process is costly because furnace is required for cooling purpose too. Normalizing is less time consuming, full annealing is more time consumption, and normalizing temperature is higher than the full annealing temperature. Annealing temperature is lower than the normalizing temperature. It provides fine grain structure because temperature is more high, but it provides coarse grain structure because lowest temperature. In normalizing, the cooling is established in air, so the cooling will be different at different locations. Thus, the properties will vary from surface to interior. But in full annealing process, the furnace cooling ensures identical cooling conditions at all locations. Within the metal, it produces identical cooling. So the properties of the material is almost similar in surface as well as the interior. So the next step is nothing but quenching. So quenching is nothing but it is an accelerated cooling. That means the cooling process, how we are cooling the materials. This is nothing but quenching. The cooling can be accomplished by contact with a quenching medium, which may be a gas, liquid, or solid. Most of the time, liquid quenching media is widely used to achieve rapid cooling. So what kind of types of quenching mediums are available? 5 to 10% of soda, 5 to 20% of brine like NaCl, then cold water, warm water, mineral oil obtained during the refining of crude petroleum, then animal oil, vegetable oil, air. So these are all the medium for quenching. Thus the water produces the most severe quench followed by oil, which is more effective than air. So comparative with air, oil and water, these two are the parameters which having a more quenching aspects and it will be more effective too. Applications of quenching medium. So mineral oils used in hardening alloy steels. So for hardening alloy steels, we are using mineral oils and quenching carbon and low carbon alloy steels like medium carbon and low carbon alloy steels for water or NaCl. Then used for rails, pipes and heavy forgings we are using for water and air. So these are all the quenching mediums that we are using normally. Then the selection of a quenching medium, desired rate of heat removal. How much heat to be removed in a particular time. So this to be the desired rate. So this has to be considered for quenching selection of a quenching medium. Then required temperature interval. So what kind of a temperature is required and how much it should be reduced and how much it should be maintained. So these things to be calculated and the boiling point and the viscosity, flash point, stability under repeated use, possible reactions when the material is being quenched, cost. So these are all the parameters that we have to consider for selection of a quenching medium. Then the stages of quenching, vapor jacket stage and vapor transport cooling stage and liquid cooling stage. So these are all the three methods of quenching stages. Then hardening, how we are maintaining the hardening by using quenching medium. Like hardening refers the heat treatment of steel, which increases its hardness by quenching. So by using the cooling rate, we can by using the quenching methodologies, we can improve the hardness as well. So hardening normally implies heat treating operations, which produces microstructures which are entirely or predominantly martensitic. So martensite. What is meant by martensite? An interstitial solid solution of carbon in ferrite. So interstitial that we know that in the first class itself that we have discussed that the interstitial solid solution. How it will be like that? Like the atomic molecules are in between the first atoms. That means first materials atoms are presented in that structure In between that molecular atoms, the second carbon, like carbon material, can be presented over there. So this is an interstitial solid solution. So objectives: to harden the steel to resist wear. Harden the steel. How? Why we need to harden the material to resist the wear? To enable it to cut other metals. Hardening by quenching. That means the operation. How hardening can be done with the help of a quenching medium. Hardening, the steel to be heat treated is heated slowly in a furnace to 30 to 50 degree above the upper critical temperature. That means we are heating the element above the upper critical temperature nearly 50 up to 50 degrees centigrade. Then soaking. The heated steel is held at this temperature for a considerable length of time. That means we are maintaining the same temperature for a particular time. So this is nothing but the process of soaking. Then the cooling. The steel is cooled by quenching, like water or oil, like this kind of a methodology that we can use in the quenching medium to the room temperature. How much it should be reduced? The temperature to be reduced up to the room temperature. The cooling rate should be higher than the critical cooling rate in order to get the completely martensitic structure. So if we want to maintain the martensitic structure, then that we have to use for water or oil medium to cool down up to the room temperature. So this is the process of normalizing. Then the factors affecting hardening: carbon content, quenching medium, and specimen size. So these are all the three important parameters. So carbon content will be affected by using the hardening process, because if we are increasing the carbon content, then the automatically hardness will be increased. So by using the carbon content, we can able to increase the hardness. And quenching medium. So quenching medium is also one of the important parameter to increase the hardness and affecting the hardness. Then the specimen size. So specimen size is also one of the desirable factor for maintaining the hardness. Other factors: shape of the specimen. So shape of the specimen is also most important, because to avoid the sharp corners and that kind of a materials may have or may development of the crack can be taken place. So these should be avoided. And quenching temperature, that the quenching temperature is most important, that how much time to be maintained for soaking, and what kind of a temperature to be reduced up to what kind of a level, and what kind of a time to be maintained in a particular stipulated time, how much temperature to be reduced. So this should be controlled. So controlled quenching rate to be there. And surface conditions of specimen. So specimen surface conditions is also one of the important parameters. Then the alloying elements. So alloying elements is nothing but that, like manganese, sulfur, phosphor. So these kind of other materials are also presented in the steel. So these should be also making some effects in hardness. So the next process is nothing but tempering. So what is meant by tempering? The martensite, which is formed during hardening process, is too brittle and lacks of good ductility and toughness. That means the martensitic structure, which is formed during hardening process, is too brittle. After completion of the hardening process, it is too brittle, and good ductility and toughness material. Toughness properties are also available, but it cannot be used for most applications. Also, the internal stresses that are introduced during hardening having a weakening effect. So this kind of internal stresses can be developed while the process, and this can be affected the material's hardness and material strength of the component. And also the ductility and toughness of the martensite can be enhanced, and these internal stresses are relieved by a heat treatment process known as tempering. So how can we reduce this kind of internal stresses can be relieved? So, and also the ductility and toughness of the martensite can be enhanced. So these two can be done with the help of a tempering process. So what's meant by tempering process? And also what's the objective of tempering process? Objective: to improve the ductility and toughness. So major important parameter for tempering process is the improving the ductility and toughness, and reduce the brittleness of hardness steel, brittleness to be reduced, and remove the internal residual stresses caused by the rapid cooling, and improved wear resistance. So these are all the parameters to be improved. For these purposes, then we are using tempering. So what is tempering? Tempering is a process of heating a martensite seal at a temperature below the erectile transformation temperature. So we know that the ejector transformation temperature is nothing but around below 738 degrees centigrade. So 250 degree to 650 degree, that we have to make it as heating the element. So after 650 degree, we can able to heat the element for a specific time period and slowly to the room temperature. So we can heat in the material and it can be maintained for, it cannot be maintained. It can be simply put it into the atmospheric air cooling. So it can be slowly cooled down to the room temperature. When the martensite steel is heated at the temperature as low as 200 degrees centigrade, the internal stresses may be relieved. So when we are heating up to the 200 degrees centigrade, the internal stresses can be relieved, and tempering heat treatment transformations martensite into the tempered martensite by diffusional process. The reaction of the transformation of tempered martensite can be written as martensite single phase to tempered martensite. That is nothing but alpha plus Fe3Cs, that is hematite phases. So this can be developed on that after completion of the tempering process. So what will be classifications of tempering? The low temperature tempering, medium temperature tempering, and high temperature tempering. So these are all the three classifications. So this can be obtained for low temperature tempering between 150 degree to 250 degree centigrade. This is a hard microstructure of martensite. This process relieves the internal residual stresses. This process is generally applied on cutting and measuring tools of carbon and alloy alloy steels. Then the medium temperature tempering at 350 to 450 degrees centigrade. This process is also increases the endurance limit and elastic limit. This process is applied for spring steels and die steels. Then the high temperature tempering like 500 to 650 degrees centigrade, it eliminates the internal stresses completely, and this process is applied on structural steels. So that we may be able to know that the tempering process can be done from 150 degree to 650 degree. That means below 738 degree, the critical temperature. This is most important parameter. So within this 150 degree to 650 degree, that the tempering process can be done. We have to understand and we have to know these temperatures clearly, because this is most important. If we cross this limit, then it cannot be the tempering process. It can be some other different processes. So that we have to maintain. Because if we cross 450 degree, then it is going for high temperature tempering. If we cross 250 degree, then it is going for medium temperature tempering. So that you may identify that based on the temperature only, we are classifying into three different categories. Then some of the hints that we are giving here, like full annealing process. The full annealing process, the temperature is 723 to 910 degree. Then the hypoelectric steel is 0.77 percentage of carbon, 30 degree to 60 degree above the eutectile line. Then the hyper-eutectile steels, that 0.77 percentage of to 1.6 percentage of carbon. Then 30 degree to 60 degree above the eutectile line. Then the cooling can be done furnace heating and slow cooling. Applications to soften the material to refine the crystallization temperature. Then the process annealing 550 to 650 degrees centigrade. Here you may identify the full annealing can be done 723 to 910. That means above the upper critical temperature. But the process annealing can be done below the upper critical temperature, like 550 to 650 degrees centigrade, slightly below the AI line. That we may understand that low carbon steels is 0.25% of carbon, already strain hardened steel, furnace heating and slow cooling, wide applications in preparing the sheets and wired sheet drawings. Then the stress relief annealing, same 550 to 650 degree centigrade, and employed to eliminate the internal residual stresses caused by casting, punching, medium cold working, and the extra, etc. Furnace heating and slow cooling, it is also known as recovery, which removes most internal residual stresses, which little changes mechanical properties and no drastic change in microstructure. So the microstructure can be maintained in the, as it is in the process annealing. Then the spiralizing annealing, temperature just below the A1 line. The medium and high carbon steels heat treated to develop the spiralized structure. The spiralized steel having a maximum softness and ductility, and also are easily machined or deformed. Furnace heating and slow cooling to soften the material to improve the machinability and formability to increase the ductility and toughness. Then the recrystallization annealing, temperature at which crystallization takes place, and furnace heating and slow cooling. There is also the process which distorted grains of cold working metals are replaced by new strain-free grains. But it cannot, here we have to understand, it cannot be make it any differences in its structure. The solid structure is maintaining as it is, but it is only having the distorted grains to the new free grains. So this to be important parameter. Then the normalizing 50 degree to 60 degree of above its upper critical temperature, then the slow cooling in air. So the normalizing process can be done in air medium, slow cooling which can be done in air, but here also we are maintaining the slow cooling, but it is in the furnace itself. Here, up to the annealing process, we are maintaining the furnace for cooling. But in normalizing, we are not having the furnace. We are going to get into the product to atmospheric conditions. To refine the grain structure, to increase the strength of the steel, to provide more uniform structure and castings and forging. Then quenching. Quenching is having different kind of mediums like water, oil, soda, mineral oil. So these are all the quenching mediums which can has been described above. And the cooling, accelerated cooling. So this kind of a quenching medium is used for rapid cooling processes. So if you are using quenching medium, the cooling processes can be done rapidly. So the mineral oils used in hardening alloy steels, water is used for quenching the carbon and low alloy steels, water and air used for pipe and heavy forgings. Then hardening the quenching. By using this quenching methodology, we can improve the hardening. Then the 30 degree to 50 degree above its upper critical temperature, and the water or oil is as a quenching medium. Then the furnace heating and the accelerated cooling. Accelerated cooling means sudden cooling. So to harden the steel to resist wear, to enable it to cut other metals. So these are all the hardening materials. That means this hardened steels are used for like tool bits. That we know that drilling HSS high speed steels and single point cutting tool, multi point cutting tool, drill bits. So these are all the things can be done with the help of this kind of a hardened materials. That means hardened steel. Then the last point is tempering. Tempering is nothing but 250 degree to 650 degrees centigrade. Then the heater can be taken place. Then the below the critical temperature of A line. This process usually follows the hardening process and slowly cooling down into the air in the atmospheric to improve the ductility and toughness, to reduce the brittleness and the hardened steel. So tempering process is also almost similar to the toughness, similar to the normalizing process. So these are all the major important hints that we have to take it in our mind while considering this annealing and normalizing, tempering, hardening processes. Thank you.